Initial launch angle projectiles. The launch angle is the angle of the initial velocity above the horizontal. It can be expressed in the terms of the x and y components of the initial velocity. Together, those create a hypotenuse of the total initial velocity. You can imagine that the x component of your velocity is how fast it's been launched horizontally, such as pushing something horizontally off of a table. The y component you can imagine as something being thrown straight up or dropped straight down forcefully. And together, they can create a total initial velocity. And this hypotenuse that forms this total initial velocity, you can imagine being what a baseball radar gun might measure as the speed of a baseball pitch, or what a police officer's detector tells how fast you're driving. It's not measuring the x and y components individually. It's measuring your total initial velocity. And that's part of the launch angle and the launch velocity. When you put an object into free fall, it moves in a parabolic shape. The objects will finish their motion moving downward at the same speed that they started moving upwards. That means that if you were to launch, for example, something upwards at 20 meters per second, that at the same spot on the downwards path, it would also be moving at 20 meters per second. You can imagine that as it travels upwards and downwards, that the velocities at each of these locations are going to be equivalent. It's like a mirror image. The only difference is that anything moving upwards is going to have a positive velocity, and anything moving downwards is going to have a negative velocity. Both sides of the arc will have a negative acceleration, however. An interesting thought exercise about this is to imagine a snowmobiler shooting a flare gun straight up vertically. Here's a very small snowmobiler and a very big snowmobile. Let's say the snowmobile is moving forward at 30 meters per second, and the snowmobiler decides to shoot a flare. If the snowmobile is in motion and maintains a constant horizontal velocity, meaning it's not accelerating horizontally or speeding up or slowing down, where will the flare land in a vacuum? Will it land in front of the snowmobile, behind the snowmobile, or in the snowmobile? You might think that it would land behind the snowmobile, but that's not true. If it's moving at a constant horizontal rate, it will actually land back inside the snowmobile. And that's because when you launch off the flare is moving forwards at the same rate that the snowmobile is. And as a projectile in the horizontal motion moves at a constant horizontal rate, if the snowmobile itself also happens to start moving at a constant horizontal rate, they'll travel the same distance horizontally in the same time, and the flare will land back in the snowmobile. There's a cool illustration right here of how that might work. And this video clip shows a professor with a sample cart acting as a snowmobile and a little ball that acts as the flare gun. And you can see as he pushes the cart forwards that the little ball pops up and lands directly back inside. It's pretty cool to watch. The range of a projectile is the horizontal distance it travels. The maximum range is going to be at a 45-degree angle. In real life, though, the maximum angle is less than 45 because of air resistance. But theoretically, in the perfect world, 45 degrees is going to create the maximum range. And any other complementary angles will land in the same spot. For example, you can see that this one right here at 60 would land in the same spot as this one right here at 30. And that this one right here at 75 is landing in the same spot as this one right here as 15. Pretty cool. Some things to remember when calculating these is that the horizontal velocity is going to be constant still. There's still nothing pulling it or pushing it horizontally. The moment you've released it, There's no more force acting on it. It becomes an object moving of its own inertia. And that's a common misconception. People think that when you push it, that you're going to continue to push it the whole way. But that's incorrect. Once you release it, that force is no longer being applied. Other than that, the vertical motion is going to be the same as a free-falling object. It's going to speed up and it's going to slow down just with gravity. This illustration right here shows that an object that was launched up, as it reaches this part of its arc, is going to have the same speed as if it was launched downward at that speed to begin with. So once they reach these two parts in their arc, they are essentially identical paths, which is kind of cool. Let's do an example calculation of something that's been launched upwards at an angle. It says an outfielder throws a ball to first baseman at 22 meters per second at a 50-degree angle. An outfielder is going to catch it at the same height from which it was thrown. How long does the ball take to get to the first baseman? So we're looking for time. We can find our time horizontally, or we can find our time vertically. Let's fill in what we know to be true always. We know that our acceleration horizontally is 0 and vertically is negative 9.8. We know that our initial velocity vertically is going to be whatever this launch value is here upwards, and that our horizontal value vertically is going to be whatever this launch value is sideways. So we're going to need to use our sine, cosine, and tangent skills to find the values of our initial velocity here and here. So this is 16.85 and this is 14.14. I'm going to fill those into the table right here. And we know one more piece of information. We want to know how fast the ball is moving right here when it reaches the first baseman. And we know, since this is a parabolic arc, that the speed at which it's launched is going to be the same speed at which it lands. So we can actually also say that the velocity vertically at the end is negative 16.85. Let's calculate the time it takes the ball to get to the first baseman. I'm going to use the information here in the vertical column. And I'm going to stare at my equation sheet until I find an equation that has initial velocity, final velocity, acceleration, and time. So the equation I'm going to choose is this one. And I get a total time in the air of 3.44 seconds. There we go. We solved our first problem. Here's our second problem. It says a pelican is going to fly in a horizontal path right at the speed of the water. Here's a pelican. As it flies, it's going to throw a fish upwards as it flies along at 5 meters per second. So it's going to throw the fish along just like this. It's going to toss it up in its mouth and then catch it over on this side. So it says the fish is going to travel a distance of 5.24 meters horizontally before hitting the water. What is its launch angle and speed? I'm going to start out by filling in everything I know about the problem. We know the acceleration is 0 and negative 9.8. We know that the pelican is flying along at a speed of 5 horizontally, which means it'll continue at a speed of 5 horizontally, and that it travels a total horizontal distance of 5.24 meters. We are looking for the launch angle and speed. That means that we are looking to find the triangle made up of the two initial velocities, horizontal and vertical, creating a total initial velocity. We don't have enough information here in the vertical column to do anything yet. So I'm going to start out by solving as much as I can by finding the time in the horizontal column and then porting it over to the vertical side. So I'm going to find time right here just so we can have a little more information in this column. And I'm going to pick this equation. So I got a total time. And this is where it becomes kind of tricky, because if you look, you might see that upon first glance in the vertical column that we don't have enough information to solve this problem, to find our initial velocity. We only have our acceleration and our time. But if you think a little more closely, you might realize that if this is a parabolic arc, that its initial velocity and its final vertical velocity are going to be the same. This is just going to be a positive value, for example, a positive initial velocity, and this will be the same number, only it'll be negative. So that means if we're going to fill out an equation such as this, that we can substitute this for and this for exactly like that, which means when we move it over to the other side, we will get negative 2 initial velocity equals AT. I got 5.13, which means in solving that our total triangle, we would have this be 5, and that our upwards value right here would be positive 5.13. This becomes positive 5.13 up, and this becomes negative 5.13 at the end of the arc. So in looking for the hypotenuse, we would do the Pythagorean theorem value of 5.13 and 5. Let's find that. And I got 7.16 meters per second as my hypotenuse. And when I used tangent to find my angle, I got 45.7 degrees. So this will be my answer, my launch angle and speed. Good work. Good example, guys. An object is launched upwards and lands at the same height from which it was launched. It travels a distance horizontally of 18 meters and a vertical distance of 4 meters to its peak before falling 4 meters back down. What is the initial launch speed and angle? Let's start by filling in what we know. We know the acceleration horizontally is 0 and vertically is negative 9.8. And we know the distance it travels horizontally is 18, and the distance it travels vertically as 4. The problem being is that if we're going from the beginning to the end, the vertical displacement of the object would actually be 0. And if we fill in 0 right here for this distance, we're not actually going to have enough information to solve this problem as much as we might try. So we might have to consider a different tactic. Think about it. What if we only calculated the first half? Then we could know our initial launch speed and angle, and then the distance horizontally to this point right here at the top would be 9. The change in position vertically upwards would be positive 4, and we know that vertically it pauses at the top. That might give us enough information to solve. Let's try it. Let's start off by looking for our initial velocity in the vertical direction, because our problem wants us to calculate the initial launch speed and angle, which are these two values right here. So let's start by calculating our initial launch velocity in the vertical direction. I got an initial vertical velocity of 8.85. Next, I want to find the initial horizontal velocity, but I can't do that without knowing more information. So I'm going to find the time in the vertical direction and then port it over to the horizontal direction. I'm going to pick the simplest equation I can think of. Which gave me a time in the first half of 0.90 seconds. That's the same in the horizontal direction. Now I should have enough information to find my horizontal initial velocity. Let's do that. I'm going to use this equation. This part of the equation cancels out, giving us just 9 equals initial velocity times 0.9. We can solve by dividing, and we get an initial velocity of approximately 10. Our very last step is going to be to calculate the total initial launch speed and angle using the horizontal initial velocity and the vertical initial velocity. We will make a triangle using the two components, horizontally 10, vertically 8.85. We'll use the Pythagorean theorem to get a total initial velocity of 13.3. And if I use tangent, I can find the angle, which is 41.5 degrees. There we go. Our total initial launch speed, 13.3 meters per second, and our total launch angle, 41.5 degrees. Nice work, fam. Let's work on some practice problems. You got this.